They're just simply groups of numbers. I just gave them human names. You know, they could represent anything. Okay, but we have 3 separate samples, each representing what we think is maybe different populations. Okay, here we go. One group is called Fred, the other group is called Jim, and the third group is called Alice. Okay, so just for starters, I'm going to find descriptive statistics for these 3 groups, these 3 samples. So I'm going to go to Analyze, Descriptive Statistics, Explore, because I want to take a look at all 3 groups. I'm going to move the measurement, whatever that is, that number 3, 2, 1, simple number, because we're going to be playing around with that number in Excel. We're going to attempt to do this calculation by hand in addition to doing with SPSS. I'm going to move that into my dependence list. In other words, that's the numerical variable that I'm going to find the mean of. Okay, and then I'm going to move my groups, my factors, into my groups into the factor list. In other words, this is the groups that I want to break it up into: Alice, Fred, and Jim. Okay, and I'm going to sneak up here to statistics, and I'm going to see, well, it's going to calculate the descriptive statistics for me, 95% confidence interval, in other words, an alpha of 0.05. That's enough for now. In plots, very frequently, because we know it's one of the requirements to do analysis of variance, we're going to want to know that these populations are normally distributed. We only have 5 numbers here, so I'm not going to bother to do the normality test or even to plot a histogram, because I know with only 5 numbers, it's going to look it's not going to look very normal anyway. So I'm not going to do those. You might want to do those when it's a larger data set and you really want to take a look at your data. I'll leave stem and leaf turned on for whatever reason. So we know that this is going to do our calculations for descriptive statistics for the 3 groups. And it's also going to do side by side, what kind of plots? Box plots, automatically. So I'll click OK. And sure enough, let's take a look at what we got. The average for Fred is 1.8. Average for Jim is 3.4. The average for Alice is 4.4. Okay, so that's a small sample though. Seems like pretty unlikely that we'd be able to distinguish between Alice and Jim, or maybe Jim and Fred, and so on and so forth, with any level of statistical significance. But we're gonna give that a try. Now, if this is all we knew, these means are all we knew, and the only tools we had to work with up to now are the ones that we have up to this point, how would you test whether the mean between the mean of Fred was different than the mean for Jim? What test would you use? I'm sorry?
That test we just learned.
Yeah, well, hang on a second. You use a t-test, right? If you just had 2 means, you use a t-test, right? Just average for Fred. Well, hang on a second. Well, why, I also can, I can do this another way maybe. Maybe I can say, let's compare Fred to Jim using a t-test, right? Well, and then let's compare Jim to Alice using a t-test, right? Well, I've left something out here, haven't I? I haven't tested Fred against Alice, so we'd have to do a t-test 3 times with 3 groups in order to test all the possibilities to see if the means are significantly different, right? If I had 4 groups, how many t-tests would I have to do? Well, I have to do the first one times each of the other, compared to each of the other 3, so that's 3. And then the second one, I've already done it first, 2. I'd have to do 6 consecutive t-tests, right? And if I were going to use a t-test to repeatedly test 2 groups against each other until I got all the possibilities done. What's the probability of being wrong when we do a t-test if we have an alpha of 0.05? 5%, right? That's kind of what we're saying is that our probability of a type 1 error, is that we're finding acceptable is 5%. Well, but what happens if I repeat that test 6 times, or 8 times, or 12 times, or 20 times? Well, it's like Russian roulette, right? Sooner or later, you're gonna, there's gonna be bullets going to be in the chamber, and you're going to be wrong, right? So that doesn't seem very acceptable, does it? Right? That doesn't seem like a good approach to this. So we need a mechanism for comparing more than one mean, the mean of more than one group to other groups at the same time, rather than doing consecutive t-tests or something like that. The one tool that we've really had to do this so far. Well, one thing that we have, at least graphically, is we can look at the box plots. And the box plots give us an idea. Can you see that behind me? Is that up there? Okay. The box plots, maybe we want to turn down the lights. Would that make it easier if we turn down the lights a little bit, or are you just looking on this? Can maybe? Yeah. Okay, great. Okay, so the box plots give us an idea of the variability of these groups, and also give us an idea where the middle of the groups are, where the mean, in this case, not the mean, but the median. And we can see there's a lot of overlap between Jim and Alice. There's some overlap between Fred and Jim. There isn't very much overlap between Fred and Alice, and so on and so forth. We kind of get a feel here that the variability can give us a clue to whether or not these samples represent different populations, right? That variability gives us a hint as to whether we're likely to be able to prove that they're different. Okay, so I'm going to play a short video now. And I'm hoping that this will work well for the guys that are online also. I'm not sure how it's going to work here either, but I may, if it doesn't work well, I may just play it from another location here. You know, just play it on from the main terminal up here. So I'm going to give this a try. And let's see. See if I still got the address. Yep. Okay. And let me see. I'm going to want to play it. Well, I'm going to crank up the sound. Let's see how this works. This is challenging. You guys that are online presumably can hear me again. The link to this video is on Blackboard. It's the first of the analysis of variance videos. And you should play it in your, you open it in another window, get the link and go over and play it. I'm going to turn the sound off here. I'm going to play this here for the people that bothered to come to school today. I'll talk to you in a little while. Okay, guys, so we're back online now, and you should be able to hear us. And we're going to go now to an Excel file that represents the same data that we just looked at with SPSS. And that's called SPSS demo for analysis of variance. I'm going to open that up. Oops, got the wrong one. That's the wrong one. Let's see here. Let's try this one. Yep, that's the one I want. That was called ANOVA Excel demo. Okay, and you'll see an Excel file looks something like this. Okay, you guys back again now, on guys online? Can you hear me again? You can see the that Excel spreadsheet I have open. Great, terrific. Okay, so let's take a look at this. Okay, first thing I'm going to do is I'm going to calculate the mean for Fred, for instance. Okay, what's the mean for Fred going to be equal to? Mean for Fred is going to be equal to, let's see what I got. What did I do here? Okay, I'm going to say the mean for Fred is equal to, let's see, it's going to be, well, actually, you know what I'm going to do first? I'm going to take all these values for Fred. I'm going to copy them and paste them down here. I'm going to take all these values for Jim. I'm going to copy and paste them down here. I'm going to take all these values for Alice. I'm going to copy them, and I'm going to paste them down here. Okay, so now I'm going to calculate the mean for Fred. That's going to be equal to the average of these numbers. Again, I just used Fred as a name for a sample. Okay, and it's 1.8. The average for Jim is going to be equal to, and you may notice that these numbers are the same numbers that we got just now when we used SPSS. 3.4. Average for Alice, parentheses, is 4.4. And now I'm going to find the variability for each of these groups. In other words, the variability for the numbers within each group, for the actual individual values in these samples. Okay, so the mean for Fred is 1.8. I'm going to put 1.8 over here, and I'm just going to copy it down. Make it easy for me to do a calculation. And I'm going to mean for Jim is 3.4. I'm going to do the same thing. I'm just going to copy it down. And the mean for Alice is 4.4. And I'll copy that down. Okay, so how do I calculate my variability? Well, I'm going to find the difference between each of these values and the mean. It's going to be equal to 3 minus 1.8, what the average is. And that gives me 1.2. I'm going to repeat that for each of these values. I'm going to copy this formula down, fill down. So these are all of the differences. The next thing I'm going to do is I'm going to square the differences. Okay, and these are each of the values times themselves squared. So they're all going to be positive numbers now. And I'm going to repeat that for each value. Okay, now I'm going to add up all of these squares of the differences between the values and the means. Equals sum. And just like we did at the beginning of the semester, for the group Jim, I've just calculated the sum of the squares of the differences. Okay, I'm going to repeat this for each one of these other guys. Oops. Okay, and that's equal to this times itself. I'm going to fill that down. Okay, a little tedious, right? But that's what we have Excel for. We're going to appreciate Excel all the more when we get done with this. Okay, again, now for Jim, I've calculated the sum of the squares of the differences. Or what we call shorthand, we call sum of squares. Doesn't matter which one I do, which one I subtract from which here when I'm taking the mean and the actual individual values, because I'm going to square them anyway, so the signs will disappear. Oops. Some of you guys are fast. I can tell some of you guys are faster than I am. Okay, sum of squares for this is, oops, left out the equal sign. Okay, so we got 17.2. Let me see now. Okay, so up here, in this little box up here next to sum of the squares of the differences within all of the groups, I just abbreviated that within. You can understand that is within the groups. The sum of the squares of the differences within all of the groups is 2.8 plus 5.2 plus 17.2, or in other words, 25.2. If I click in there, you'll see that it's just E16 plus E24 plus E32. Okay, so now the next thing I want to do is I want to figure out what would the degrees of freedom be here. Okay, well, the degrees of freedom for the numerator in our, for our denominator in analysis of variance, that's going to be equal to the number of subjects for all of the groups minus the number of groups. So we got 15 subjects, we got 3 groups, so the degrees of freedom is going to be equal to 12. 15 minus 3 or 12. Okay, well, this box that just filled itself in is just the mean sum of squares within the groups. By mean sum of squares, I mean basically the sum of squares for all of the values in all of these groups divided by the degrees of freedom. That's not so different from the variance when we calculated it before, right? We divided by n minus 1 degrees of freedom. In this case, we're dividing by n minus the total n1 plus n2 plus n3 divided by 3, but it's analogous to what we did before. So this represents the mean sum of squares within the groups. Remember down here we said f is equal to the mean sum of squares between the groups and over the mean sum of squares within the groups. Well, down here we've filled that value in. It's now 2.1 is the number that we're going to use on the bottom. Okay, so the closer together these numbers would have been, the smaller this number on the bottom would have been. Make sense? Because that would mean all the differences would be smaller, the squares would be smaller, the adding them together, the sum would be smaller, and we divide it by 12, and this number would be smaller. The more the variability, the bigger that number is. And the bigger that number is, the smaller f is. Right? So the deal here is we want f to be large, because f means, when f is large, it means that our probability of there being not enough difference between these groups for us to reject the null hypothesis we're going to discuss in a second, right? Means that f needs to be further out on that line, that value for f, to get to the very tail of that distribution. So we have less than a 5% chance of being wrong if these groups in reality, the means of these groups in reality are the same. Okay, so now let's do the next part of this. Now we want to find the sum of the squares between the means themselves. Okay, so let's click in here with that 17 point, let's see. Okay, 07. I think this shortcutted a little bit. Oh, here we go. Oh, actually, I already filled it in before. It's already filled in. Okay, the overall mean for all 3 groups, in other words, the mean for 1.8, 3.4, 4.4, for all those groups, the overall mean was 3.2. Now I'm looking at the variability between the means. I'm looking at the means themselves as a group of 3. Okay, so the means are 1.8, 3.4, 4.4. The difference between 3.2 and 1.8 is going to be minus 1.4, plus 0.02, and plus 1.2. So that's the difference between each of the means and the overall mean. Okay, so I'm going to square that now for 1.6, 0.05, so on and so forth. Now I'm going to also multiply that by 5, the sample size within each group. We got lucky. I could have just averaged these. We got lucky because the sample sizes in all 3 groups are the same. Not always going to be that way. This will account for different sample sizes. So the difference is squared. 9.8, 0.2, 7.2 is 17.2. Now that represents my sum of squares of the differences between the means, and Now my degrees of freedom, what do you think my degrees of freedom are going to be? So now I have, yeah, it's going to be 2, n minus 1. The sample size is, the means are, there's 3 means, minus 1 is 2. I'm going to put a 2 in there. It's going to divide into that 17.2 to give us our mean sum of squares. Again, a measure of the variance between those 3 numbers, between those 3 means. And that comes out to 8.6. That goes on the top of our value for F. So what is F? What's the statistic F? The analysis of variance. What's our statistic mean? Calculate. What do we calculate it to be? Well, we calculate it to be 8.6 over 2.1. Okay, or 4.09. Okay, so now when we were dealing with the t-test, right? What did we use to determine whether our statistic was large enough to reject? Now that we're at this point, let's bring up the null hypothesis. We have 3 means that we're trying to distinguish between to be able to prove that there is a difference between the means of the populations that each of these 3 samples are drawn from. So what do you think the null hypothesis might be? Right? They're all equal. Mu1 is equal to mu2 is equal to mu3, or mu Alice is equal to mu G. And again, we're interested in the means. We use mu, not x bar in each case, because we're trying to prove that the means of the populations are different. We already know that there's a little bit of a difference between the samples. There's always going to be a difference between the samples. But the point is to prove that they're different. Okay, and our alternative hypothesis is going to be that there's a little bit tricky here. They don't all have to be different. Just at least 2 of them have to be different. That there is some difference between the means in these groups. Okay, so our F statistic is 4.09. So now where do I go to find out whether or not that's big enough? We need a table, right? Unless we're using SPSS or R or some other software, I'm going to need a table. So I'm going to need a table for analysis of variance. Okay, here we go. I'm going to open this table up. Oops, wrong table. Wrong table. Hang on a second. I must have it on Blackboard, right? Is there a table on Blackboard? Yes, here it is. I got it. Okay, here's that distribution that we were looking at before. 0, and here's the value of F. The larger the value of F is, the further to the right that we can go. And what we're interested in is values of F that are so large that the probability of all of these means being from the same population, the probability of that occurring gets smaller and smaller and smaller. It's the area that remains to the right of F. So in our case, F is equal to 4.095, I believe it was. So now you'll notice that we have degrees of freedoms listed here in rows and columns. The columns represent the number of degrees of freedom between the means. What was that? That was 2. So we're going to be looking down this second column. Had we had 4 groups, we would have been looking down the third column. Okay, and what about the degrees of freedom within the groups? That was 12, if I recall correctly. So what's the critical value of F that we have to exceed to reject the null hypothesis? And do we? Yes. We do. So what do? We reject the null hypothesis and we accept the alternative hypothesis. Yes?
You got the degrees of freedom for 1 and degree of freedom for 1. How do you use the table for that?
Oh, I'm sorry. Okay, yes. Okay, so now, I'm sorry? If it's not, is it on Blackboard? I thought
It's in your brochure about ANOVA.
Oh, okay. You know, I'll make sure it's individually in there as a separate table if you want to print it out. But what I have is I have columns and I have rows. The columns represent the degrees of freedom between the groups, right? Between the means. The rows represent the degrees of freedom within the groups. Okay. The rows are going to be a larger number. Right? The means are going to be a smaller number. So we only have 3 groups. So the number of degrees of freedom is 2. So we're looking exclusively at the second column. right? And then we're gonna, if we had a very large sample, we might be down to 120 if each of the groups had, say, 3 groups with 40 or 4 groups with 30 people in them, and so on and so forth. We'd be looking down here. If we were comparing 6 groups, we'd be looking at the column with 5 degrees of freedom. Okay, so in our case, 2 degrees of freedom across the top, right? And going down here to 12 degrees of freedom within the groups. Okay, 15 minus 3. So that's 3.89. We reject the null hypothesis. Okay, so now, obviously, if we have large sample sizes, if we have much more complex numbers, this is going to be pretty tough to do with Excel. So we would prefer to be able to do this with statistical software like SPSS. So let's open this same file in SPSS. And I have that down here as SPSS demo for ANOVA. In fact, we had it open, didn't we? We had it open already from before. Okay, so I'm going to go to Analyze. What are we doing here? What is our purpose here? What are we trying to do? We're comparing what? Means. We're comparing means. Even though it's called analysis of variance, we're comparing means. So I expect to find this in compare means. I'm going to go down here to one-way analysis of variance. Don't worry about one way for right now. One-way analysis of variance. I'm going to click on that. And again, it's going to ask me for my numerical variable, my dependent. I'm going to put measurement in there. And I'm going to break this up into 3 groups, my factors. Now, for
It's
now,
7 o'clock.
for now, thanks. For now, I'm only going to look at this calculation. And I'm going to click OK. Okay, here comes up my output window. And let's see what I've gotten here. The sum of the squares between the groups was 17.2. Looks familiar, right? Same number we calculated. The degrees of freedom is 2. So the mean squares, the sum of squares divided by the degrees of freedom, kind of like the variance between the means, is 8.6. Exactly what we calculated. The sum of squares within the groups, all at the different values, all added up together, all the differences squared, is 25.2, and the degrees of freedom are 12, just as we calculated. So the mean squares within the groups is 2.1. So if I go over to F now, we can see that F is just simply 8.6 divided by 2.1. And in fact, when you do more complex analyses, you're actually going to see that same relationship. You'll see that it's always going to be the mean squares between the groups divided by within the groups is going to be the F statistic. Okay, and you're going to see the calculation done just as you would have done it by hand. Well, now, Excel has all of these tables built into it. So instead of giving us a critical value for us to compare against, Excel actually gives us a probability, a p-value, of having a type 1 error with this data. So in this case, instead of looking to see if my F statistic is did I say, what did I say? No, I meant SPSS. Yeah, well, okay. I'm excited. What can I'm all excited.
Wow, it's more than I ever thought.
I'm all excited because most semesters I don't get the calculation right. It doesn't come up the same. So at any rate, so all that excitement now has got me all rambunctious, so I'm getting mixed up. So at any rate, where before we had to use the critical value F to decide whether or not we could reject the null hypothesis, this time Excel SPSS is actually giving me a probability of a type 1 error, a p-value. And what do we want that probability to be less than to reject the null hypothesis? Less than the alpha that we chose to begin with, presumably, which was 0.05. And is it less than 0.05? Yes, it is. So I can reject my null hypothesis. Okay, so we're going to take this one step further. Hang on just one second. Just have to take care of something real quick.
I'll tell you something interesting about the F statistic that I forgot to mention. That is in the 2 sample case, the F statistic is just the square of the T statistic, and you get the same p-value if you do an F test compared to doing a T test if you have 2 samples.
a matter of fact, I have a great example of a great example that we do some semesters we've done in the past, where you use the analysis, you do both tests. You get you take two samples, it means we have the data for the two samples, and we compare the means using the t-test, and then use the same data using analysis of variance. You get exactly the same result. Okay, so you're really kind of doing the same thing. You're looking at the variability and looking to see how far apart the means are based on the variability. So, okay, so now what have I done now? I've rejected my null hypothesis, which is what? That the means are all equal. And I've accepted my alternative hypothesis, which is that they're not all equal. However, what's missing here? What have I not done? I've not demonstrated which ones are not equal, right? We don't know. Is Alice, at least two of these are different, right? Since we got that result, is Alice different than Fred? It looks to me like there's a pretty good shot based on the box plots that we're going to find that Fred is different than Alice. But now, is Fred is statistically different? Do we have enough evidence to say that Fred is also different than Jim, or that Jim is different from Alice, and so on and so forth? We need to do something. Now that we've completed an analysis of variance and we know that there is some difference that we can demonstrate here statistically, we need now to do another test, a post hoc test. After post hoc meaning after the fact. So we need to do more tests here. Okay, so now we can go into Excel and go to Analyze. I'm going to repeat the same analysis. Compare means, one-way analysis of variance, except this time I'm going to click on post hoc, and a whole bunch of weird things are going to come up here. And these are all different methods for testing within the 3 groups or 4 groups or 5 groups for searching out where the differences are in the mean that you discovered using analysis of variance. Well, if our F statistic had been less than 3.89, or if we got a p-value of greater than 0.05, would I be here now? No, I wouldn't, because we weren't able to prove that there was any difference between any of the means, right? But now, having proved that, now we're interested in proving which ones are different. Well, why are all these strange methods here? Well, because we have to avoid that problem that we had before with the t-test, which is if we repeatedly do the same test over and over again, we're increasing our probability of being wrong. So these tests are basically mechanisms for adjusting for that. One of them, I forget which one, is basically just taking that 0.05 and dividing it up between the different groups. In other words, if you're going to do the test 3 times, then it's adjusting that 0.05 so that, you're really looking for whatever, 1.66. 0.0166 or something like that, and then adjusting it upwards and giving you a p-value that would have been equivalent, right? So that one of them is that simple. I don't remember which one. I think that might be Tukey. Is that Tukey? Oh, at least squares? Whatever. Doesn't matter. For whatever reason, Bonferroni and Tukey are 2 of the most popular of these post-hoc tests. You can do multiple of them if you want. I'm going to do both. I'm going to check off Bonferroni and Tukey, and I'm going to have it test all these different combinations for us. Actually, I'm going to do one first. I'm going to do Tukey first. And I'm going to click Continue. And SPSS is going to repeat the same analysis, okay, except this time, in addition to calculating my analysis of variance and my significance, it's also going to compare each of these groups to one another. Okay, so it's going to compare Fred to Jim, and it's going to find that the probability of a type 1 error is 0.229, right, above our tolerance for type 1 error. Fred versus Alice is 0.037. What does that suggest? That suggests the mean for that group, the group Fred versus the mean for Alice, is statistically significant, right? There is a difference there. You'll notice that it does a funny thing where it repeats all of these twice, right? Fred and Alice is here, but it also does Alice and Fred down here. It gives you the same result, of course, but it just repeats it twice. It goes through every permutation. So what about Fred and Jim? Doesn't seem to work out, right? How about Jim and Fred? Same result. How about Alice and Jim? Nope, that doesn't work out at all, does it? So Our post hoc test suggests that the only two groups that are statistically different are Fred and Alice. Okay, our analysis of variance confirmed that there was a difference between some of the groups, and our post hoc test told us which one or which ones had a significant difference.
And it's because the significance values are
Less than?
is smaller than 0.05.
Correct, right. It's less than our tolerance for error, less than our tolerance for a type 1 error. Okay? All right, good. So now, let me see what I can come up with now. Okay. So now let's try another example of this. I'm going to go back here. And now these examples are uploaded as a homework. Okay, let me find the lab sheet. Let me just check out this over here. How are you guys doing online? Is that clear? Did that make sense to you? Online people? Okay, good. Oh, we got some responses. Excellent. Okay.
Kinda.
Kinda.
Kinda, okay.